Hello, in this video we're going to learn about implicit differentiation, which is the same as finding the derivative. It's just got a little bit of an extra steps, extra twist to it. So an implicit function is when y is not by itself. There's a mathematical way of saying it, but it's just y is not alone. What we're going to do is we're going to implicitly differentiate, which just means that we're going to find the derivative like we always do. But as we go along, we're going to encounter y's. And whenever we encounter a y, we're going to kind of pretend, okay, that's my inside function, and then apply the chain rule to that y, and then just mark it down as y prime. So let's look at an example. We want to implicitly differentiate this thing. And we've got d squared y and dx squared. That means we're going to find the second derivative of this as well. So you can see x and y are not on separate sides. They're kind of mixed together. So we're going to find the derivative of each term. And what kind of helps, especially when you're first doing this, is to actually write out, okay, I want to find the derivative of that x squared. Actually, I'm going to get a little closer. There we go. I want to find the derivative of that x squared. Then separately from that, in my head, I want to find the derivative of that y squared. How that's going to work, deal with that in a minute. I'm not doing that right now. All I'm dealing with is just writing down what I want to do. I want to find the derivative of each one of these terms. And that means we've kind of been skipping over it, but we also want to think about, hey, we've got to find the derivative of the other side as well. Kind of like think about if you're multiplying both sides by something, we're doing the derivative of both sides of this equation. So they're really just kind of like solving equations, this implicit differentiation. So I want to find the derivative of x squared. Easy peasy, lemon squeezy. That's 2x. Done. Okay, now when I go on to find the derivative of y squared, I want to apply the chain rule. So I would find the derivative of just like a squared. So that would be a 2. I would keep the y and then reduce the exponent by 1 to make it a 1. Then I would need to find the derivative of the inside. So the derivative of y is y prime. So this d over dx is y prime. Or remember what the thing is looking for. It's looking for dy over dx. So this derivative of y and this y prime thing, it means the same as dx. dy over dx. Cool, that's the thing that we're looking for. Hooray! Then this equals the derivative of 1, that is 0. Now, again, they were looking for that thing we were looking for, dy dx. It's right there. It's right there. So let us, I don't know why there's a tick there. There shouldn't be a tick there. If you're thinking that's like a y prime. Oh, that's a 1. That's the exponent of 1. Okay. So we want to get that dy dx by itself in order to figure out what dy over dx equals. That was a terrible sentence. We're going to just take this 2x and we're going to slap it over on the other side. Okay. So now we've got 2y dy over dx equals negative 2x. And then I want to get rid of that 2y. So just divide both sides by 2y. And we end up with dy over dx equals negative 2 over 2y, which is really just negative x over y. We're done. We found it. This is dy over dx. Great. Note that I didn't have to bother solving for y or nothing. You never will solve for y when you're doing this implicit differentiation thing. Now, it did say that we also want to figure out what d squared y, what this thingy is. We were looking for this as well. Okay, well, all right, sure. So that's just asking us to take the derivative. So d over our derivative with respect to x of that cool thing that we just found. Negative x over y. Okay. So, all right, well, let's do that. Okay, well, that is a quotient, right? Notice that I didn't do one for the top and one for the bottom because in the original, I did it for each term. So I did it for the x squared, I did it for the y, I did it for the 1. But I didn't do it for the x and the squared. I just did it for the x squared. That negative x over y, that's just one term. So just in that one term, let's do quotient rule. So quotient rule on the top, derivative of negative x is negative 1, multiplied by y, minus the derivative of the bottom. Well, that is going to be dy over dx again, multiplied by the top, which is negative x, over our denominator squared. Okay, well, that's y squared. Easy. All right. Well, there we go. We've got it. We figured out what d squared y is, but it's a little goofy, right? Because it's got this thing in it. It's got that dy over dx, which seems a little weird. Well, hey, we know what that is. We just found it, didn't we? It's that dy over dx again. So it's this. We can actually plug that thing in and use it to help us find our second derivative. Oh, how cool. Thank you very much. So we get d squared y over dx. Let's clean this up. This is just going to be a negative y minus, well, I'm going to make it a plus because we've got this minus minus. And then we've got still the x, and that's going to be multiplied by that first derivative thing that we found, that negative x over y. Negative x over y. And then this whole thing is over this y squared. Okay, let's just do a little bit of cleanup to finish this off. Multiply those x's together, they become x squared. So we get negative y plus negative x squared over y. And then this whole thing is over y squared. I don't really like that fraction in the fraction, so let's multiply everybody by y. So this equals negative y squared minus x squared over y cubed. Oh, can I circle? What is this? I don't want that, whatever that is. There we go. Cool. That is our d squared y over dx, or our second derivative. Our first derivative was that negative x over y. But we found it implicitly by doing it term by term and not getting that y all by itself. Let's try another. In this example, again, we're going to implicitly divide this thing because we got y's all over the place and I cannot be bothered in order to get that y by itself before I find that derivative, because it's asking for the tangent line, so that's asking for the derivative, but the x's and y's are all mixedy goofy together. So let's just find the derivative of each term one by one. So I am going to do the derivative d over dx of 6x squared plus the d over dx of 3xy plus, and again, I like to write all of this out so that I can kind of see what I'm trying to do. Because then it's just like, okay, I mean, there's a lot of goofy things happening, but I'm just trying to remember what I'm trying to do. I'm trying to find the derivative of each one of these terms. Okay. And then I can kind of think about each one at a time, because some of them might spiral into something goofy. So I don't want to, when I get back to that thing, it's like, wait, what am I doing again? Oh yeah, derivative. Got it. Now the other side is, well, no. I have to do the derivative of the other side too. I just couldn't fit it all there, but that's okay. Well, I'm going to do that easy one, d over dx, that's 0. And that's easy. Then this piece, d over dx of negative 6, that's also 0. Easy. I'm going to go over here now because I want to get the easy ones done. Derivative of 6x squared, that's going to be 12x. Okay, I'm scared of the red one, so I'm going to skip that for right now. I'm going to move back over here to the orange one. And now we have to do one where we need to do chain rule. So our outside of function is sort of a multiply by 7. We've got an exponent of 1. We would drop the 1. And so we would get 17 Just a 17, no inside part because that y would get an exponent of 0, multiplied by the derivative of the inside, which is a dy over dx. So again, that y didn't show up because it was there, but it was a y to the 0. And y to the 0 is just 1. So I did use my chain rule there. Let's do the green one. So I would do chain rule. So I would drop my exponent, and it would become a 4 and a y to the 1. Remember, the other one, it was a y to the 0, so it went away. And then we need to do the derivative of the inside. So the derivative of y, well, that is dy over dx. Great. All right. No more putting it off. It's time for the scary one. This is a product rule. We've got this first term. I'm going to put the 3 with the x. You could put the 3 with the y, but y is already goofy enough as it is. So we got a 3x and we've got a y. So we need to use product rule on that thing. So the derivative of 3x, that's 3, multiplied by our second, which is y, plus the derivative of y. So, well, that's going to be dy over dx. Kind of like what happened with that 17. But now there's no 17 anymore. Times our first, which is 3x. Woohoo! We did it. Okay, now we want to figure out what the value, we want to find the line when we're at that point, negative 1, 0. Negative 1, 0. And before, what we were doing is we always just had y and x, but we kept like just plugging in the x value. But look, I've got x's and y's now. So it's a good thing they gave me that full point, because I'm going to put both of those in. So I could do some algebra to try to clean this thing up, but I don't really care to solve it. I just want to figure out what dy over dx is. So why clean it when I'm just going to like put some constants and stuff in there? So we've got 12 times negative 1. I'm just going to do this all in purple. Plus 3 times our y value, which is 0, plus dy over dx. I don't know what that is, but that's what I want to find. Times 3 times my x value, which is negative 1, plus 4 times our y value, which is 0, dy dx. Again, I want to figure out what that is, but I don't know what it is yet, because that's going to be the slope of our tangent line. 17 dy dx plus 0, so gone, equals 0. Okay, let's see. All right, so we've got negative 12. Well, let's see, 3 times 0, that's just 0, so later, minus 3 dy dx. This is going to be a big 0, so later, plus 17 dy dx equals 0. Let's bring the 12 over to the other side. So we get 12 equals, let's see, that's going to be 14 dy dx. See how I kind of treat it like a variable in like terms? And then divide both sides by 14. So our slope is 12/14 or 6/7. Now that's what they were, well, it's part of what they were looking for. They were looking for the tangent line, but that's just the slope of my tangent line. So now I need to put it into an equation. Now they did give us a nice y-intercept. Is that y-intercept? No, that's an x-intercept. Never mind. That's our x-intercept. Okay, so let's see. Our tangent line is going to be at y minus 0. So that doesn't really make sense. And then 6/7 x plus 1. So that is our tangent line. Quick reminder of normal. Normal is just perpendicular to our tangent line. Whoop. So normal. So y equals negative 7/6. and then the same coordinate point. All set. And I think that does it for us. So implicit differentiation is just meaning that y is not by itself. So we need to treat it basically like a chain rule as we work our way through the problem. A reminder that our derivative of y is just y prime, but a lot of times we'll be writing it as like a dy over dx. Either one works. Thanks for watching. Bye bye.